recording. The 30 or so people who aren't here can have something to do. So we're recording now. This is our last module. This is module 11.2 on ethers. So this is a continuation. They run hand in hand with the alcohols, because we can make ethers from alcohols and we can make alcohols from ethers. And as we saw last time, we actually had a special ether, the epoxy, that let us make diols and other things. All we had to do is hit it with a nucleophile and it would create this wonderful stuff. And so we're going to continue on that and talk about some of the other ethers that aren't that cyclic ring system and how their properties are actually very different than what we saw in the cyclic three-membered ring system. Okay. So, and for those of you who are watching this video, we have a group activity on Monday with a review, and we also have our third exam on December the 2nd, which is a Wednesday. Okay. I see a hand up. Yes, Marcy.
Hi, Dr. Urban. I had a quick question. So I was watching the recording from last class, and I noticed that you had must have forgot to record the first half. Would you be willing to post a mini lecture of just the slides that weren't recorded, just for those who missed class last time?
That's a great idea. I can do that. Yeah, because it turns out I did forget to start recording, and I was probably only 10 minutes in. So I can do a mini lecture on that to do a supplement. So it'll go under that Zoom meeting supplement, and I'll redo those slides. So that's
Perfect.
a great idea. I'll get that up today. That'll be great.
Okay, thank you.
All right, so I'm going to go ahead and share my screen. Ask questions, of course. The chat room's open. I have the scatter view up here. Everything seems to be recording just fine. I rebooted my computer a couple times, so nothing's glitching. All right, so this is our last module. This is the last thing we're going to do this year. And then, but we are going to do an activity that kind of summarizes all the different types of reactions we have coming into our final. Now, this table we're going to be building next time is going to be very important for next semester to remember all of these reactions, because next semester we're going to add new reactions, and then we're going to do multi-step synthesis where we have to remember the reactions from this semester. So that's why I like to cap off the year with that activity where we build a reaction table. And that reaction table, number one, helps you study. Number two, will help you next semester correlate all these things together. Okay, so that being said, let's go with the last few reactions we're going to learn here, and it's all about ethers. Okay, so the ether functionality is a little different from the alcohol functionality because we don't have that acidic hydrogen on there, but that also makes it a really good solvent to do reactions in. It has no acidic salt, it has no acidic hydrogen. It actually has very few things that react with it. It's very strong to very strong bases. It's resistant to most nucleophiles. And that's because the leading group would have to be an alkoxide. And the alkoxide is a very strong base, making it one of our poorer leaving groups. That's why it's so resistant to those nucleophilic attacks. Now, under most mild acidic conditions, it actually does do fairly well. However, if you heat it with a strong acid, you can open the ring. And that's the one reaction that you can't do in ethers. But everything else, Grignard reactions where you can't have water around, that's a great solvent to use. When we did the selective oxidations with systems where you didn't want water in, ether or THF would be a great solvent for that. So it's just when we get to these strongly acidic things, especially acidic solutions with water in them, where they start to react. It's not very fast, but it reacts enough to make it a problem in the reaction. Okay, so in general, don't forget to go back and learn how to do ethers. If they're cyclic ethers, you'd give it the whole name. If they're unsymmetrical ethers, you say ethyl, methyl, in alphabetical order. If they're symmetrical, you just do di-something ether. Okay, don't forget, that's in chapter 2. And don't forget, we also have a review page on our Canvas site for all the rules for nomenclature. That's going to come up mostly during the final, by the way. All right, so when we have these ethers and they are reacting with a strong acid, specifically a strong acid in the presence of water, we can get cleavage. And what happens first is we get the, of course, creation of the oxonium ion. Okay, now in all these systems, the creation of the oxonium ion makes the leaving group a better leaving group, right? It leaves as a neutral molecule, and our new, in this case, bromide acts as our new nucleophile, our new conjugate base, can come in and displace that neutral alcohol as our leaving group. That's why it works so well in these acidic solutions. Without that protonation, you have a very bad leaving group, okay? Now, what this does do also is that it relies on the nucleophilicity of that conjugate base created, okay? Which means that HI, or the iodine, is going to be much more nucleophilic than bromide in the presence of water. Remember, that's the halides reverse in order of nucleophilicity in the presence of water, or in the presence of without water. So remember that difference there. And so now we have iodine being much stronger than HBr, and that's much, much stronger than HCl. So it's really hard to cleave these things in HCl, but it does happen, and it does happen slowly. Okay, so, and what you can do is, if you generate one equivalent of this alcohol and one equivalent of this alkyl halide, that alcohol can still be disproportionated by having excess HBr around, because if you had excess HBr, it would protonate that alcohol, giving you the oxonium ion again, and then the bromide can come in and have water as a leaving group. Okay, that's why if you have excess of your acid, you can get all the way to only having alkyl halides. Okay, so this will also works in sulfuric acid, but the more commons are HBr and HI. Okay, so that's one of the few reactions that ethers do. The rest of the time, they don't do that. Okay, so how do we make ethers? Okay, so the best way to make an ether is to just do what, a regular nucleophile electrophile attack, so that you have to have some form of an oxygen nucleophile. And the oxygen is always going to be the nucleophile, because the oxygen likes to have that negative charge on it, and that stable negative charge makes it a good nucleophile. In this case, the alkoxides are not only strong bases, but strong nucleophiles. However, if the nucleophile starts getting bulky, if that alkoxide starts getting bulky, the nucleophilicity drops. So you won't, it's very difficult to make like a T-butyl ether version of this, where you're trying to displace something. So keep that in mind. Bulkiness makes it work less readily. The other thing we need is we need a good leaving group on the other side of the ether, okay? So good leaving groups can be anything that are really nicely stable, like iodine and bromine. Those are really nice and fluffy, and so they're really good and stable. But we also have a couple other leaving groups that we're going to introduce in this particular chapter, of the sulfonates. Remember those last page or so of the last notes? We made these sulfonate and these sulfonate esters. These sulfonate and sulfonate esters are even better leaving groups than iodine and bromine, because they can more readily stabilize that negative charge. Okay, so the basic reaction is typically an SN2 reaction, where we have our, let's move to red here for today. We have our alkoxide acting as our nucleophile. We have our halide, in this case, acting as our leaving group. And we just have a nice little SN2 reaction, so we get inversion of stereocenter there. And it goes to form our ether. Now notice it says that this intermolecular reaction, or reaction between molecules, is slow. Okay, so let me put a pin in that. Let's go to the next one and talk about that one for a minute. If you can create your alcohol and create that alkoxide on the same molecule with your leaving group here to form a 5-6, particularly 5 and 6 membered rings form fast, but you can do it with 4, 5, 6 membered rings. And that happens as an intramolecular reaction within a molecule, and it happens very fast, okay? But it's still an SN2 reaction, okay? So the good old-fashioned nucleophile, attacking The electrophile is the slow reaction, but the one that's intramolecular is faster. Why? Okay. So if we think about it, remember if we have to look at our reaction diagram that you make your alkoxide over here and you have your other material dissolved in your solution, and they have to move around, diffuse around, and find each other and have enough energy to get to that transition state, right? So we have a diffusion force pulling them together or apart, and then they have to have the right amount of energy when they get there, okay? So that having those few collisions that are in the right location and the right energy is why the reaction is slow in comparison, okay? Now, let's look at the other one. All right, once we form the nucleophile here, once we deprotonate our alcohol, it doesn't have to diffuse away. All it has to do is have enough energy to close the ring, okay? So because we don't have these two molecules drifting apart or being hundreds or not thousands of nanometers away from each other, these are literally 10 angstroms away from each other when they're formed, and that means their likelihood of collision is much, much higher. So in almost all cases, these intramolecular reactions are much faster, assuming you're forming, a ring that's not too strained, because it doesn't have to wait for the other molecule to be in the right place with the right energy at the same time. Okay, that's one of the keys with these fast ring closing reactions, is it doesn't have to diffuse. It's already made. It's ready to go right when you make it. Questions on that? Okay, so that's called the Williamson ether synthesis. And we can really enhance the selectivity. It typically forms 5 and 6 membered rings. However, if you use a really good nucleophile, like something that's not in equilibrium, like I'm about to talk to, you can actually make 3, 4, 5, 6, and even 7 and 8 membered rings. However, entropically, thermodynamically, the 5 and 6 membered rings are most favored if you can. But the other rings can be made if you have what we call an irreversible base. Okay, so an irreversible base means that you use something that cannot go back between the alcohol and the alkoxide. Okay, so for example, if we took this alcohol and added something like sodium amide or sodium hydroxide, we could deprotonate some of that alcohol, but some of it would still be the alcohol, and so it'd go back and forth with equilibrium. Okay. However, if we use something that does not allow that for that equilibrium to form, we can actually make the reaction go much more efficiently and form 3, 4, 5, 6, 7 membered rings. Okay, so what's an irreversible base? Well, we learned in that reduction of aldehydes and ketones chapters that we have a new nucleophile at our disposal, which is the hydride. Okay, so the hydride is our hydrogen with our 2 electrons on it, so it's a negative charge. So if we use our sodium hydride as our nucleophile, as our base here, what's going to happen is our hydride is going to react with our proton to generate hydrogen gas and our salt of our alcohol. Once you generate hydrogen gas, it boils out of the solution, and therefore it has no equilibrium. All you have is 100% of your nucleophile, okay? And we have it in the absence of water, that we're using a solvent called DMSO, dimethyl sulfoxide, which is a polar aprotic solvent. So again, it cannot be in equilibrium. We have 100% of our nucleophile available for reaction. And so that nucleophile is going to attack the first group it can find it'll leave to generate our ether. Okay. Now, again, because we're not in equilibrium, because we have 100% of our nucleophile reacting there, we now have enough entropic energy to get to our 3 and 4 membered rings. Okay. And we're going to talk about actually 3 and 4 membered rings in a minute. Okay. So since the intramolecular interaction between the nucleophile and the electrophile are so close to each other, it happens very quickly because that it doesn't have to diffuse, it can be attained really quickly, and that we have a lower entropic cost, okay, which means that we have one molecule going to uh, two molecules, okay? So that means we have increased our entropy on our system, okay? Our alcohol with our bromide on it was one molecule. By deprotonating that and closing the ring, we now have our ether and our leaving group. So we've added a little entropy to our system, which makes it favorable. But it's also favorable because it is very close together and very easy to close that ring. Now, within all of these reactions, we do have competing reactions, especially if you have both functional groups on the same molecule, okay? So if you did this in a very low concentration, such that once you form the alkoxide, it could only find the tail of its own reaction, you would have a predominantly cyclic process. However, if you did it in the case where it maybe wasn't as concentrated, you have an opportunity for your alkoxide to, instead of tacking its own tail, to actually drift over and attack the leaving group on another chain, okay? So all intramolecular reactions are in competition with intermolecular interactions, okay? Now, why is that a problem? Well, it's a problem because if we have that, then we're going to end up with these extended chain systems here instead of the cyclic ring that we were looking for, okay? Now, they are slower reactions to form these intermolecular reactions, so they are byproducts in the system, but they are also, they're always in competition with our system, okay? Especially when we're using a reversible base. Okay, so the other thing that can happen in this case is instead of the base deprotonating the alcohol, the base itself can act as a nucleophile. And if the base itself acts as a nucleophile, then that would end up creating a dialcohol species. And that dialcohol species now is, number one, cannot form that intramolecular interaction because we don't have a good leaving group. And now it must chain extend and form that non-cyclic version. So then it's another competition that can happen in the presence of that hydroxide nucleophile. Again, a lot of that goes away when we use that irreversible base, such that that proton transfer creates 100% of that alkoxide at one time. Okay, so let's use this synthesis to make less than those 5 and 6 membered rings, okay? When we make those less of those 3 membered rings, like the epoxies and thing, we actually have to have a particular orientation of the molecule of that rotation to make it happen. If your leaving group and your alkoxide are not anti to each other and staggered, you have a difficult time forming that 3-membered ring, okay? So let's take a look at what that looks like. And I want to show you this one first right here. So in every one of these orbitals we have, these are sp3 hybridized orbitals. And there's the big orbital that's bonding, but then there's this little backside. And that little backside is not bonding to it. And sometimes it's called the anti-bonding right here. But there is a little bit of electron density there, okay? So what can happen is that we can now, if it's in this perfect anti-position, notice that this bond between the bromine and its anti-bonding position is exactly parallel to the oxygen sp3 hybridized orbital. And that gives us an opportunity for when we use these electrons to come in and make a new sigma bond here, we now have a perfect backside SN2 type reaction where our leaving group leaves at 180 degrees from where the nucleophile is attacking. Okay, so that makes it a special form of that sp2 reaction. Okay, but it only happens when you wait around long enough for it to be in this anti-configuration such that we can have that leaving group at 180 degrees from where the nucleophile is coming into attack. So what's going to happen is it's going to go back and forth between protonated and deprotonated until it finally gets to this point here. Once it gets to this point here, it has an option of getting reprotonated or closing the ring and producing bromide ion. So bromide ion is going to come out here at the end. Okay. So once we form that in the presence of water, that bromide ion is supported and goes away or gets diluted out, and we're left with our three-membered ring. Even though there's a significant ring strain here, the fact that we can still close the ring with that SN2 reaction will drive it forward, even though we're adding a whole bunch of energy to the system. Okay. All right, questions on that? So we have to actually wait for the molecule to rotate around. We have to wait for that rotated molecule to be deprotonated. And then once it is, we have an opportunity to do a very fast intramolecular SN2 reaction. So it works best with really good leaving groups. All right. So that's one way to make it. But the other way to make it is actually to start with an alkene. Okay. And so by using a per carboxylic acid or a carboxylic acid with an extra oxygen on it, we can completely avoid that having to do that wait around for that anti configuration to happen. And we can do a direct oxidation of the alkene. Remember, your alkene is electron rich, and so it wants to react with with electrophiles, right? Because it itself is a nucleophile. And in this case, the extra oxygen in these peroxy carboxylic acids is the electrophile. Okay, so let's take a look at that. And again, we're just doing it in a ring here to show you stereochemistry. So in this case here, if we drew out our Lewis dot structure for our per acid, we would see it has this kind of structure here. Okay, so what it can form is this nice little 5-membered ring intermediate, and we have a whole bunch of these oxygens here are actually electrophilic because they don't want to share the oxygens with themselves because that's a fairly nonpolar bond, and it has a polarized bond here as well. So basically this is more electrophilic than the oxygen that we would find on water because of the difference in polarity of the bonds. Okay. Which that means is that we can have the electrons from the pi cloud come up to that oxygen and create a new sigma bond. While it's doing that, we actually have, let me erase a little bit here. Okay. Now that we have this here, we can have the electrons from the pi bond create a new sigma bond with that oxygen. When it's doing that, that means that we can break the bond with the other oxygen and we can move those electrons to form a new carbonyl. At that same time, since that carbonyl would have, this carbon would have 5 bonds on it, we can actually move these electrons out to grab this hydrogen, leaving 2 extra electrons on that oxygen, okay? But we used both of those electrons from the alkene to make that first sigma bond, so that second carbon is actually electron deficient. So we can use that last set of electrons to come in here and create another sigma bond. So now both carbons have 4 sp3 hybridized bonds on them, okay? So notice right here, when we look at the electrons here, these green electrons were the ones that were in the sigma bond. These yellow electrons here are the ones that were bonding the per oxygen to the hydrogen. And these last 2 electrons were already on that oxygen. Okay. And when we form our new compound here, we have a new carboxylic acid. Notice that's exactly right. It's a COOH. So it is completely consumed in the reaction to make that epoxy. Okay. So, and what's cool about that is just like other three-membered rings, it only attacks one side and creates our three-membered ring, which means now, whichever side it attacked is, you have to come in the other side to open that ring. All right. So now we have two ways to make epoxies, and we have ways to make both long chain ethers and cyclic ethers. Okay. So the Williamson ether synthesis will make either of those things, long chains or rings, but the per-oxycarboxylic acids are very specific in making only the three-membered ring epoxy. Okay. Oh, I should tell you, this is a very common version to do this. It's called MCPBA, which is metachloro benzoic acid. So metachloroperbenzoic acid, this right here is probably one of the more common ones because this is a very stable compound and it dissolves in a lot of solvents. Okay, questions on making epoxies? Okay, now, when we talked about SN1 and SN2 reactions, we talked about how the OH group was a bad leaving group because it was a very strong base, and how the alkoxide is also a fairly bad leaving group if you don't have a stronger base available, okay? So what we're gonna do in the next few slides is we're gonna trick it to make oxygen a better leaving group. And we can do that a bunch of different ways. And the common way is to, oh, no, I'm sorry, we did that last one, sorry, we're doing protecting groups. Okay, sorry, change gear. Okay, so let's say you wanted to do a reaction that required a non-protic solvent. Like let's say you want to do a Grignard, but your product has an alcohol on at the end. You couldn't just use that reaction with the alcohol, or else it would decompose your Grignard reaction. Or let's say you want to do an oxidation on one part of the molecule, but not on the alcohol. So the alcohol would easily oxidize, right? So how can we change the reactivity of the alcohol to protect it so that we can do additional reactions? And the number one way to do that is to turn them into ethers, but not any ethers. We want ethers that are easily converted back to alcohols. If we just turn it into an alkyl ether, we'd have to hit it with really strong HBr to get it to break apart, and we would generate alkyl halides out of it. So we're using this different group to generate our protected alcohol in a way that we can remove it easily. And you'll see why it's removed easily when we get to that step. Okay, so the net result here is we definitely don't want those pesky hydrogens being around there in the alcohol, because they're easy to oxidize and they'll easily quench other reactions. So let's protect it. Okay, so what we're going to do is the first way we're going to do is we're going to make an ether with this isobutylene. Okay, so isobutylene is an alkene. You're saying, well, okay, so we're going to add water across an alkene. Exactly right. We're going to use acid catalyzed addition of an alcohol across an alkene. Okay. So when we do this, of course, we're going to follow Markovnikov's rule. And the hydrogen on here, let me draw the hydrogen in blue right here, is actually going to end up on one of these methyl groups here. Okay. And we're basically just adding our OH across that double bond in acidic conditions. Okay. So we're going to be able to, first of all, we're going to add our proton, just like we do on all of our acid catalyzed reactions. We're going to form our carbocation. Notice the reason we're using isobutylene, because it's giving us a tertiary carbocation. So that makes it really, really easy to form. Okay. Now that we have our tertiary carbocation here, we can wait around for our poor nucleophile to come in and create our oxonium cation. And then when this regenerates the acid catalyst and dumps it on something else, we end up with our neutral ether. Okay. Now, the other thing that can happen is it can actually react with another version of itself. This is electron rich, this is electron poor, and this would end up polymerizing and making longer and longer chains. Luckily, that side reaction is minimal, so we actually end up making the majority of this. But the key here is we're going through a carbocation intermediate. That's how we're generating that tertiary carbon that has the alcohol. Now, that carbocation intermediate comes into play when we try to break it off as well. Okay, so a common way to do it would be to just, you have your, you've made your reaction, you've done whatever reaction you wanted to do on the other side of the molecule, and now it's time to take it off. Well, the cool thing is that you can just use your acid catalyzed hydration to clip off that ether with an intermediate being that carbocation. And because we have acid and water present, our carbocation ends up turning into a tertiary alcohol. Okay, so if we look at that stepwise, we're going to protonate our oxygen here like we do with all of our acid catalyzed systems, creating our oxonium ion. That generates a good leaving group because it leaves as a neutral alcohol and generates our stable tertiary carbocation. Sorry, more stable tertiary carbocation. That carbocation can wait around until it gets hit by water, the only one of the nucleophiles we have, which will generate the alcohol. And then the reaction is complete. We have two alcohols. They're fully protonated because we're under acidic conditions. Okay, so we put it on with acid concentrated. What this means is concentrated acid can be 97% sulfuric acid with only a little bit of water in it. Now, if you take that same reaction, just add water to it and heat it up, we now have enough water around to act as our nucleophile and will actually clip it off. So we use the same acid to make it or break it. The only difference is when we're trying to break it off, we add excess water. And notice it says dilute aqueous acid. All right, questions on that? So that's one really cool way to protect an alcohol. Okay, and it's via an ether synthesis. Okay, so how can we use this to our advantage? Okay, so if we just did the Williamson ether synthesis using this molecule, the intramolecular interaction is much faster than the intramolecular interaction. So we'd actually end up with a byproduct in it, okay? So what we really want to do in this is we want to somehow take the alcohol out of the equation to start with, okay? So for example, if we had this alcohol present and we added our base, we're going to create aryl alkoxide, and we're going to end up with forming a lot of that because it's such a fast SN2 reaction. We're going to form some of this linear chain because that's a pretty fast reaction. Or we can actually have attacked by this alkoxide over here, generating a different version of that ether and alcohol system. So this would be a really messy reaction if we were trying to get to this product here. Okay, so we're using this not only to deprotonate this, but we're also using it as the nucleophile to displace the bromide. So this is the one we want, but we have these two compounds in our mixture. So let's change the chemistry such that we only get one product. And the way we change that is we protect this alcohol. Okay, so by just doing the simple reaction where we have the isobutylene in our system with our concentrated sulfuric acid, this only reacts with this side. It doesn't affect the bromide at all. And we end up with a very high yield of this protected alcohol. Okay, now that we have this protected alcohol, when we hit it with a strong nucleophile, notice this is also in very basic conditions. Ethers are very stable to very basic conditions, so that it doesn't react. And we actually use this as the nucleophile to displace the bromide to generate our diether here. But the reactivity of these two different ethers is very, very different. This would only clip off with strong aqueous acid like HBr. However, because we have the isobutylene group here, we can use dilute sulfuric acid to create that carbocation and then eventually react it with OH to get to our alcohol and our desired product in very high yield. Okay, so do we see the value? This is the beginning of where we're going to start going with next semester with multi-step synthesis. How can you get the most product of the desired product just by changing the sequence of reactions and or using a protecting group? Okay. And in this case, alcohols are really, ethers are some of the most common ways to protect alcohol groups. What do we have? Okay, almost there. So I said ethers are the most common, but there's not just carbon-based ethers. There's also the silicon-based ethers, and we call these silyl ethers. Okay, now they're really good because they are also very resistant to nucleophiles and electrophiles, and they're fairly resistant to acids too. However, they are very reactive to the fluoride ion. So if you have you can have a silane ether on there, you can clip it off in very mild conditions with just the fluoride ion. So let's talk about that. So if we have our alcohol here, I'm gonna blow this up, and we have a 3 methyl groups and a chloride, okay? That makes the chloride our leaving group. We do a nice SN2 reaction with our oxygens, electrons as our nucleophile. That'll generate our oxonium cation intermediate, and we have chloride as a base, and we also include a base in here, triethylamine as a base, and this can deprotonate this to give us our neutral silyl ether plus our salt. Our HCl has bound with the triethylamine to create a salt in the solution, and depending on the solvent, that'll actually precipitate out. Okay. Now, this bond right here, this silicon oxygen carbon bond, is actually pretty stable to most bases, a lot of nucleophiles. But acid and fluoride ion are the two things that will clip it off very quickly. So let's talk about the fluoride ion one. The most common way to clip it off is use tert-butyl ammonium fluoride. Now, tert-butyl ammonium fluoride, if you can imagine, is just 4 butyl groups on, those are butyl groups, making that nitrogen positive, and that's counterbalanced with fluoride ion. Okay. Now, the reason they use that is that the tert-butyl ammonium is soluble in a lot of different organic solvents, non-polar aprotic solvents, polar aprotic solvents as well. So it's used a lot in the system because it's very soluble. But the cool thing is that the bond strength between the silicon fluorine bond is much, much stronger than the bond strength between the oxygen silicon bond. And so what happens is when you have your fluoride act as a nucleophile, the best leaving group is going to be this oxygen anion. And this oxygen anion leaving is going to be an irreversible process. And we generate our oxygen anion that's counterbalanced by the positive ammonium group here. And then when you work it up with a little bit of acid, you protonate your alcohol and you generate your final product. Okay. So we're using all of our, nucleophilic and bond strength chemistries to help show us where this is happening. Now we can do this with acid because when you have your acid, you can protonate your silicon oxygen carbon bond. And when you protonate that silicon oxygen carbon bond, it makes it into a neutral leaving group, which makes it a good leaving group. And then you end up with a silicon with an OH on it, a water on it, and then it can decompose right there. Okay, so we see how to make the ether. Use the silyl ether, the silicon protected ether, using our SN2 reaction and a little bit of base, and we clip it off with fluoride ion or acid. So base to make it, it's stable to a lot of nucleophiles, and then we hit it with fluoride or acid, and we can protect it. Okay, so why would you want to do this? Well, let's say you want to do a Grignard reaction, and you have this compound with a carbonyl compound and an alcohol in it. If you added your Grignard to this reaction, it would deprotonate the alcohol, and the reaction would quench and be done. Nothing, you would not react that carbonyl at all. So instead of that, we know we want to react this side here, but we have to get rid of this acidic proton. So to get rid of this acidic proton, what we're going to do is we're going to make it into that protected group. And that trimethylsilyl is commonly called the TMS group, not to be confused with the TMS group we use in NMR, that's tetramethylsilane. But TMS chloride right here has this chloride group as a leading group. And we typically use a base like triethylamine in it. And when we do that, it does not react with the carbonyl. It only reacts with that alcohol to create that silyl ether. And then the cool thing is that we can now do our Grignard reaction, and it'll react selectively with that partially positive charge on the carbonyl. And then it turns out we always work up a Grignard reaction with acid anyway to break up the magnesium complexes. So that clips off the group here. So we're adding one extra step in getting selectivity of reaction on just that carbonyl group. So that's the power of using protecting groups. And those power of protecting groups are very important in multi-step synthesis. All right, let's see. What are we looking at? Oh, just about. And that is my last slide on ethers. Okay, so we have linear ethers, we have cyclic ethers, we have ethers made to be easily removed because we have we can form a carbocation, a tertiary carbocation, and we have a new bond we haven't talked about, which is the carbon-oxygen-silicon bond that gives us our silyl, sorry, there's an I there, a silyl ether as a protecting group. All right, so that's all I have for chapter 11. Okay. And do you see why we're actually adding this ether group right at the end of alcohols? Because we learned how to do all this stuff with alcohols, convert them into aldehydes and ketones, and we know we can react one faster than the other. And so we can have aldehydes and alcohols or ketones and alcohols on the same structure. But now, by using these ether protecting groups, we can now do selective chemistry on either side. All right. So let me go ahead and stop recording, and you can freely ask questions.